Good day everyone, my name is Divya. Today I would like to represent my topic, which is round robins. Before I begin with the exercise, let me explain a bit about round robin. Round robin is a simple way to manage tasks or distribute resources fairly. Imagine you have a group of people sitting in a circle and you want to give each person a turn to speak. Instead of letting one person speak multiple times in a row, you go around in a circle, giving everyone one chance before starting over again. This way, everyone gets a fair turn in equal intervals. In computing, round robin works the same way. For example, if there are several tasks for a computer to do, it will give a little bit of time to do each task in order and then circle back to the first one. This ensures that no task has to wait too long and everything gets done in a balanced way. In short, round robin is like taking turns in a fair, repetitive order. Let's begin with the exercise. This is table 5.1 that we will be using. To convert the given scheduling scenario into a round-robin format, we need to define a time quantum, or a time slice, for the processes. Since they didn't specify a time quantum for us, let's assume the common value is 4 milliseconds. This is how the process would be organized. We begin by rearranging the process details from process, burst time, arrival time, and priority. And then we start with the round-robin scheduling with the time quantum of 4 milliseconds. We begin by the Gantt chart construction by using the processes of P1 to P4. And then, after we got those answers, we will use them to create a Gantt chart. After that Gantt chart, we will create a completion time which involves P1 as 24 milliseconds, P2 as 11 milliseconds, P3 as 38 milliseconds, and P4 as 40 milliseconds. And then we will create a table for turnaround time and waiting time. To count the turnaround time, we will have to minus the completion time and the arrival time, while for the waiting time, we need to minus the turnaround time and the burst time. So after we have done those calculations, we get for the turnaround time, process 1 is 24, P2 is 3, P3 is 37, and P4 is 34. While for the waiting time, P1 is 15, P2 is 0, P3 is 23, and P4 is 24. To summarize all of this, the average turnaround time, we have to calculate the average turnaround time, which involves adding all 4 of the given processes' turnaround time and dividing it by 4, where we will get 24.5 milliseconds. As for the average waiting time, we have to add up all of the processes' waiting time and divide it by 4, which we will get 15.5 milliseconds. That's it from me. Thank you.
Hi everyone, today I will be presenting on the non-preemptive shortest job first SJF scheduling algorithm. We will explore how this algorithm works and how it can be applied to a set of processes to optimize CPU scheduling. My name is Surendran. The non-preemptive shortest job first algorithm is one of the simplest scheduling techniques used in operating systems. Its main principle is to select the process with the shortest burst time for execution, but only among the processes that have already arrived. Once the CPU starts executing a process, it runs to completion before moving on to the next. Let's start with the problem definition. We are given 5 processes, each with its own burst time, arrival time, and priority. Our task is to use the non-preemptive SJS algorithm to determine the best execution order. The processes are as follows. Process P1 has a burst time of 9 ms and arrives at 6 ms. Process P2 has a burst time of 5 ms and arrives at 0 ms. Process P3 has a burst time of 6 ms and arrives at 4 ms. Process P4 has a burst time of 4 ms and arrives at 8 ms. Process P5 has a burst time of 3 ms and arrives at 9 ms. In this algorithm, the key is to look at the processes that have arrived and select the one with the shortest burst time. It's not preemptive, meaning once a process is selected, it must complete execution before any other process can start, even if shorter job arrives in the meantime. Now let's look at the step-by-step process selection and execution at execution. At time 0, only P2 has arrived. Since it's the only process we executed P2 first, after P2 completes at time 5. P3 has the shortest burst time among the arrived processes, so it is executed next. By the time P3 finishes at time 11, P1 is the shortest available process, so it runs next. At the time 20, both P4 and P5 have arrived. Since P5 has a shorter burst time, it executes first. Finally, P4 is executed after P5 finishes. Here is the Gantt chart which illustrates the order and timing of the process execution. P2 execute from time 0 to 5. P3 execute from time 5 to 11. P1 execute from time 11 to 20. P5 execute from time 20 to 23. P4 execute from time 23 to 27. This chart helps us visualize the CPU time allocation based on the non-preemptive SJF scheduling. Next, we calculate the important performance metrics. Turnaround time (TAT) is the total time from when a process arrives to when it completes. Waiting time (WT) is the time a process spends waiting in the queue before execution. For each process, these calculations are as follows. P2 has completion time of 5 ms, a turnaround time 5 ms and no waiting time. P3 finishes at 11 ms with a TAT of 7 ms and a WT of 1 ms. P1 finishes at 20 ms with a TAT of 14 ms and a WT of 5 ms. P5 finishes at 23 ms with a TAT of 14 ms and a WT of 11 ms. P4 finishes at 27 ms with a TAT of 19 ms and a WT of 15 ms. The average turnaround time across all processes is 11.8 ms. The average waiting time is 6.4 ms. These values shows the efficiency of the non-preemptive SJF algorithm for the given processes. In conclusion, the non-preemptive SJF scheduling algorithm is effective at reducing waiting times, especially for processes with shorter burst times. However, there is a risk of longer process being delayed or staffed if many shorter processes keep arriving. This makes it important to weigh the pros and cons of the algorithm depending on the workload. Thank you for your attention.